Hello, welcome to the second part of these two lectures on earthquakes. So in the first part we looked at, we defined what earthquakes are. We saw that they occur along fault lines in the earth and movement along those faults, displacement to build up of stress and strain in the rocks. Then as frictions overcome and you have a sudden movement along that fault line and a release of energy, and sometimes huge amounts of energy. And that energy comes out in the form of seismic waves. And we learned about seismic waves, and we learned how seismic waves are used to locate earthquakes. We used the difference between P and S waves, if you can remember. We learned about how we measure the size of earthquakes in terms of intensity, the intensity scale, which is a measure of essentially how much destruction in buildings takes place. And we learned about the more scientific, if you will, measurement of the energy released, something called, what was called the Richter scale, now it's the moment magnitude scale. All right, so the second lecture, what are we going to cover? So we're going to go through the different types of earthquake destruction, the main one being collapse of buildings from ground shaking. It's very much a mantra people talk about in earthquakes, and when they talk about earthquakes is in that buildings kill people, not the actual not the ground shaking. It's the buildings which kill you, not the earthquake, if you will. We'll go on to talk about other types of effects of earthquakes, such as liquefaction of the ground and subsidence, which then occurs, lowering of the ground surface. All these secondary hazards which are caused by earthquakes, like landslides and fires. Often, for example, gas lines and pipes are ruptured during an earthquake, and they can ignite and cause fires. Also, fires from electrical cables, etc., being snapped. And tsunamis. Tsunamis are very much caused by one of the main triggers of a tsunami is a seabed earthquake. We'll then talk about earthquake prediction. When can you, or when, where, how large? We'll talk about, in terms of earthquakes, can we predict when one will occur, where will it happen, and how big will it be? That would be the goal with all of these hazards, be they volcanic eruptions or in this case earthquakes. We'll talk about long-term predictions, so is a likelihood or probability of an earthquake occurring over the next decade or a few years. And short-term prediction, which is sometimes a lot more useful to you and I. Will the earthquake, is it going to happen in the next week, the next 2 weeks, for example, or tomorrow, if you will? We'll discuss that and show the viability of that. And finally, we'll finish off by talking about earthquake hazard mitigation. How can we reduce the risks? Word mitigation. Well, what can we do? And in terms of a community, as a town or city, and what can you do individually as well? All right. So earthquakes are major causes of fatalities and deaths every year when large earthquakes occur. We mentioned in the last class, you literally get thousands of earthquakes every year throughout the world, but most of them are very, very, very small and only affect a small radius around them and relatively low on the magnitude scale and really cause very, very minimal damage. But you do get also large earthquakes, and this slide shows some of the notable ones over, especially during the last century, the early part of this century. For example, in China, 200,000 people died. So we're talking about in the tens of thousands, or even the small, sorry, hundreds of thousands of people may, sorry. It can result in that sort of numbers of deaths, much more than really most of any other natural disaster, especially if you include tsunamis with earthquakes, for they also cause this sort of death toll. Other notable earthquakes include the Mexico City one from 1985, Kobe earthquake in Japan was a big one back in the 90s. At the end of the 1990s, 1999, there was a major one at a place called Izmit in Turkey, just about 80 miles south of or east of Istanbul, the capital there, and about 20,000 plus people died in that tragic event. Indonesian tsunami and earthquake. It was a tsunami caused by an earthquake, and the figure here, but it's actually the figure that goes up to something like over 200,000 people lost their lives. It was the largest natural disaster in modern times, the Indonesian tsunami. The Haitian earthquake more recently, back in 2010, around about over 100,000 people died from that one. I need to revise that figure. And the Japan earthquake, the largest earthquake in Japanese history, a 9.2 on the magnitude scale, as was the Indonesian tsunami one, by the way, but it was about 9.2. So huge earthquakes. But the one in Japan, the largest in Japanese history, that one and the Indonesian tsunami earthquake and the Japan earthquake, they were so powerful. The actual planet, you could actually measure it. It actually ringed, if you will. It vibrated and moved a few centimeters, and you could measure that. And there are many, many more. So, and they're still happening in recent years. So they cause a lot of damage, and the main cause of certainly human loss of life is from building collapse. So it says here the mantra I mentioned: earthquakes don't kill people, buildings kill people. So it's not the earthquake. If you're out in a field, an open space, a parking lot, whatever, and you live through an earthquake, it's going to throw you around a bit, but it's nothing going to fall on your head. You're going to be safe, essentially. But in towns and cities, that's where the destruction and the loss of life occurs, and injuries. It's from buildings collapsing on people. Examples of that here you can see in China, the top right. China, the most seismically active country in the world, the amount of earthquakes it has in that one nation. On the bottom left, the Loma Prieta earthquake from 1989 in California, Northern California, and that was the last big sized earthquake. I think it was about 7.0 on the magnitude scale to affect the San Francisco region. The epicenter was a little bit south of San Francisco, a place called Loma Prieta, but also it caused some devastation or some collapse of buildings, notably this freeway, this double-decker freeway in Oakland, sort of just east of San Francisco. And we'll come back to that, but that was the only source of the only people who died in the Loma Prieta earthquake happened at this photo, where this photo shows this freeway, and about, I think it was 59, around about 60 people lost their lives, those especially underneath the lower store of that when it collapsed on itself. But there's a reason why it happened. In talking about earthquake destruction, there's a reason why some places have lots of destruction and others don't. And we'll come back to that, but basically it's one of the key things is building codes. So if you have very high building codes, in other words, buildings that are designed to withstand ground shaking, like they are in Japan, like they are in California, near the San Andreas Fault, they are now in many parts of the modern cities of China. They're built to a very high standard, so and lots of places in Southeast Asia. So buildings, even skyscrapers, can withstand huge earthquakes now, and they're designed to flex and move, and they will stay up. They are not going to collapse anymore, the modern structures, during a very large earthquake. But in countries where they don't have those resources or haven't to put into their infrastructure, unfortunately, buildings will collapse still, and quite readily, and cause the destruction like you had in the Haitian earthquake of 2010, where essentially the whole capital city of Port-au-Prince collapsed. So destruction from shaking and building collapse, it's caused by these seismic waves or seismic vibrations destroying houses and infrastructure. So the amount of structural damage depends on, you can think, three variables. Firstly, simply the size of the earthquake, so the intensity and the duration of the earthquake. Some earthquakes are only literally just a second. Others can be sort of many seconds, maybe up to a minute. Not quite the 5 minutes you see in Hollywood movies. You don't really get them lasting that long. Secondly, the nature of the material can affect the amount of structural damage. So the nature of the material upon which the structure rests. And as we'll see, earthquakes on bedrock as opposed to the same earthquake, as the seismic waves pass through an area of bedrock as opposed to an area of, say, sediment, behave differently. We'll find out that sediment actually amplifies an earthquake seismic wave and will make the vibrations as it passes through soft sediment or an area underlain by soft sediment like mud or silt, etc., compared to a solid bedrock area. And lastly, what I was just talking about in the last slide, the design of structures and building codes. So obviously, buildings which have been designed to withstand earthquakes don't fall down so much, unless it's a very, very large earthquake. So that very much, the design of structures certainly affects the amount of structural damage. Generally, the amount of damage occurs, it gets less with distance from the epicenter. So here it says the regions within 20 to 35 miles of the epicenter will experience about the same intensity of ground shaking, and then gradually it dissipates at the surface with distance. Here to illustrate this image again of the capital city of Haiti back in 2010 during that tragic earthquake, that really catastrophic type of natural disaster, sort of natural disaster on its biggest scale, and a tragic loss of life. Numbers vary, but typically it's normally sort of the figures given around about 160,000 people in Port-au-Prince and neighbouring areas lost their lives. Mainly because of what you see in this photograph. Buildings collapse, as you can see here. This was a 5-story building, say, and it's just like a pack of cards. So anyone in there really has very little chance unless they happen to be in sort of a pocket space. But and you can see the building materials they're making. That they're very, these buildings aren't designed to withstand. They're just built out of these cinder blocks, these breeze blocks. They're not built to withstand earthquakes. So that's what's caused the death. Buildings collapsing in, for example, Port-au-Prince here in Haiti. 7.0, a big earthquake, but not huge, not massive, but yet it's one of the largest natural disasters in the last 100 years in terms of fatalities. So it wasn't a massive earthquake. That Loma Prieta earthquake, which I've mentioned near San Francisco in Northern California, that was also about a 7.0. I think it was a 6.9, but it's about the same size. Huge difference, so, in what happened. There's two clips here. I'll ask you to look at these in your own time, but please do, though. The first one, both relate to the Haitian earthquake of January 12th, 2010. And the first one is a news article one day after the aftermath of that earthquake. So newscasters on the ground showing immediately what had happened. And then the second one is a kind of a review of 10 years on, telling the story of the earthquake again and looking back and seeing how much the country of Haiti had recovered. So do have a listen to both of those, please. Okay, so I mentioned the subsurface has an effect on the amount of structural damage, be it on see if it's underlain by solid rock or sediment. So this slide gets into that subject. So earthquake destruction, spatial pattern of damage. So the pattern of damage caused by earthquakes is not uniform, but depends on the properties of the underlying rock material. Waves, so seismic waves, are amplified. In other words, they get bigger by soft rock and non-consolidated sediments, so sands, muds, etc. But these waves are subdued, smaller vibrations, in other words, by solid rock as it passes through an area of solid rock. So a great example here is from data from the Loma Prieta earthquake of 1989. So here we're located on the main map on the east side of San Francisco Bay, around the town of Oakland. Shows in the star there the epicenter, by the way, was at Loma Prieta, some distance south of San Francisco. And on the map it shows these three colors. The kind of sort of hard to see on your screen, maybe sort of pinkish color on the left. That's what it describes as Holocene Bay mud. So it's essentially soft, unconsolidated mud on the edge of the bay itself. Further inland, you have an area underlain by quaternary sediments, so sands and gravels, somewhat more compact. And then higher up in the hills, this part of California gets quite hilly quite soon, and you get bedrock, underlain by bedrock, mostly sandstone, it says here. So 3 seismographs, 1 in each type of material. So the first one, A, is located in the muds, and there's a seismogram reading, and you can see it's the largest amplitude of the wave, so the strongest vibrations. B is located in the older sediments, and it's here you can see it's dampened, there isn't much, it's subdued somewhat compared to the mud, and you can see less ground vibrations. And C, up in the hills of above Oakland, near Berkeley, you can see the much more reduced vibrations. So it's here, and this is where that photograph I've shown of the double-decker freeway, the highway had collapsed and caused the fatalities. That was a place called the Cypress Viaduct, and that was located just above through over the top of these muds. So that's why it collapsed. Even though it was some distance from the epicenter, Loma Prieta, it was that building, it was that structure, that highway, which its foundations went and collapsed due to large vibrations being amplified in that bay mud area. So it was a direct consequence of the underlying material and the collapse of that structure. So my advice, if any of you, life takes you out to, for example, live in an earthquake-prone area, let's say the San Francisco Bay region, try and get a house in the hills, in the with solid rock underneath. So maybe have a look if you end up living in an area with earthquakes, at a geological map and say, hey, this neighborhood's underlain by rock. That's good. We'll move there. Okay, that was ground shaking. Another type of earthquake destruction is something called liquefaction. So liquefaction is where unconsolidated materials, so sands, for example, are become saturated with water and turn into a mobile fluid, like quicksand. So areas of sand, when they're saturated, unconsolidated materials have little spaces called pores in between the grains. And groundwater can, after a heavy rain, will percolate through those sands and fill the spaces, make that sediment saturated, fill all those pore spaces with water. And that, when a wave goes through it, when a seismic wave goes through this saturated material, it'll then behave like quicksand, and things will sink quite readily. Structures, for example, buildings, will sink into the ground. So they allow structures to subside or topple into the ground, literally. So the ground turns to quicksand, buildings will sink, but then the particles themselves, when they settle after the earthquake's passed, and they kind of consolidate. So this slide shows the particles of sand or gravel. They have a sort of tighter packing, so the ground surface therefore has subsided. So you often see areas of subsidence occurring after this, which also, can cause damage to buildings as well. Here, image from the large earthquake that struck Mexico City, the 1985 Mexico City earthquake. And here you can see the structure, it's stayed intact, but it's actually sunk into liquefied ground. Mexico City is essentially built on a bowl-shaped lake bed, a dry lake bed, but an ancient lake bed with sands and silts and muds. And those sediments, especially the sands, became saturated after several weeks of heavy rain, just prior to the earthquake. So it was kind of bad luck in that regard. And these sands, when the earthquake struck and the seismic waves went through those layers of sand, it turned it into quicksand, and the buildings collapsed, sunk into the ground, like you see here from liquefaction. Another example of that here from the largest earthquake in North American history, which was struck Alaska in 1964, not far east from Anchorage, in Alaska. And this was a 9.2 earthquake, a massive earthquake, in other words. One of the largest earthquakes of the 20th century, and like I say, the largest one ever in North American history. And here on the left is an old photo from Anchorage, and you can see the main street, the high street here, has subsided. So the ground, in other words, became liquefied, and then it's subsided after that. All the grains and the loose sediments repacked at a more compact way, and you can see probably subsided, I don't know, about 3 meters, so maybe 12 by 10 feet or so, following this earthquake. So earthquakes cause a lot of secondary hazards as well, such as landslides, especially in areas, with hills, with slopes, which can be maybe after rain as well. They're already unstable. Then you have ground shaking, and that's when you often trigger landslides. There were hundreds, literally hundreds, after the Loma Prieta earthquake, small landslides, and this photo is actually from Northern California, from that event. And these small events, if there was a property, a building in the path of this landslide, it's obviously that's going to be destroyed. But roadways, railroads, etc., they can also be kind of taken out by landslides. So they cause each of these things significant amounts of damage. And like I say, they can often be triggered by earthquakes. Another example here of a train tracks, a railroad being undermined here by a collapse of the ground, in this case. Earthquakes very much cause fires, so they can cause fires especially from broken gas lines or broken gas mains, gas pipes, and once they become ruptured, they can ignite and cause a fire, and they're very, very, very difficult for the emergency service, the first responders, to put out as well, especially because sometimes the water lines that run to the fire hydrants, they've been broken as well, ruptured, so it makes it very difficult then obviously to extinguish them. You rely on just the appliances themselves, the fire trucks. They can rupture fuel tanks, so large, for example, storage fuel tanks on oil farms, etc. And they can down electrical lines as well, and they in turn can cause fires from these downed electrical cables being snapped. If you remember, we can see how when earthquake waves go through, they can expand and push, expand and collapse, and that will snap cables quite effectively when that happens as this concertina of a seismic wave goes through. So they make them difficult to extinguish by the ruptured water lines I mentioned, but also damaged roads and things laying across the road. So it makes it very difficult for first responders to get in there to a fire to then put it out. And in that time, buildings around can be burned essentially. So this can all overwhelm the emergency response facilities. These sort of issues, and they're a real headache. They still happen. Like more, they cause more damage often than the actual ground shaking in many places where buildings are built to a high building code. So the buildings might not collapse, but you're still going to get broken gas lines and therefore fires. This photo on the bottom is from the Northridge earthquake of 1994. Northridge being just not far north of the city of Los Angeles, of LA. Here in the background of this slide is San Francisco, and this is the great earthquake of San Francisco, 1906, I think it was, or 1904, 1906, I believe 1906. And here the gas lines had just been put in, state-of-the-art, technology for the city, for the proud residents of the city. They've just got this gas. You can see a gas light on the left-hand side of the photograph here. And these gas lines were ruptured, they were ignited. There were many wooden structures in this building still then, and you can see from the great billowing clouds at the back, smoke. The city was burned essentially, was in flames, and that caused actually a lot more damage than the actual building collapse at the time. They also caused tsunami. So earthquakes, we're not going to talk too much about tsunami in this lecture. It really deserves its own lecture, but just briefly, seabed earthquakes, so offshore seabed earthquakes, if you have a type of earthquake with a vertical displacement, so a normal or reverse fault, which will displace the seabed vertically, that especially occurs at subduction zones where you have one plate sliding underneath and subsiding on the other, and as it does so, it pulls down a bit of the overlying plate, and eventually that springs back. And when it springs back, it sends a shock wave through the water that causes the water to ripple out in all directions. And when that wave, which travels at very, very high velocity in deep water, but a long wavelength, so you actually wouldn't feel it if you're in deep water. It just quickly goes through, not very high, but very long wavelength. But when it gets to the shoreline and shallow, and what waves do they call touch bottom, and the bottom starts to basically slow down the base of that wave. It slows down, and this long wavelength wave starts to pile up. The wavelength gets less, and the water piles up, and you can end up with a wave 20 feet, 30 feet, 40 feet, even recorded up to sort of 90 or 100 feet during the Indonesian and the Japan tsunami locally in some areas. And cause huge destruction. This image at the back of this slide is the Japan tsunami from 2011. This event took, I think about 16,000 people died, which is actually, compared to, say, the Indonesian tsunami, where over 200,000, a low level, because of there was a warning system in the Pacific where people were told to evacuate. They had 30 minutes or so to evacuate, and they knew the drill to do that in their schools and workplaces that they practice at. And people evacuated, fortunately, and they also have large, sometimes tsunami walls around the main towns. They could be sort of 20, 30 feet tall, some of these walls. But anyway, here you can see it's inundating the low-lying area of Japan in this case. So these destructive tsunami waves cause widespread coastal flooding, triggered by undersea earthquakes. There are other triggers. Watch the tsunami lecture to find out about those. In the open ocean, the height, as I said, is usually less than a meter. Didn't sound much there, that's kind of, it can be kind of less than a normal sea wave caused by wind. But in shallower coastal water, the water piles up to heights can be over 30 meters, 100 feet, massive at its largest. Here is where waves got very big. It's this Indonesian tsunami. The bottom right shows the destruction at the place called Banda Aceh in the northern tip of Sumatra in Indonesia, which is right near the epicenter of this earthquake that took place offshore from the island of Sumatra in Indonesia. And this city, these people, you can see two residents returning to the city after the event to see if anything, their belongings are there, and the whole city was completely almost wiped off the map. And the earthquake, with tsunami wave, would have been higher than those tall palm trees you can see in the background of this image on the bottom right, for example. The wave was actually higher than those, so completely destroyed the city and the neighborhood, the towns of Banda Aceh and elsewhere. It affected about 14 countries. The Indonesian tsunami, all the way around the rim of the Indian Ocean. Basically, the wave propagated across to Thailand, which is shown on the top photograph here, also across to India, and caused many deaths in those two countries, Thailand and India, and Sri Lanka as well. But here in Thailand, you can see the waves coming in, and unfortunately, people didn't know much about it. A lot of tourists are there as well from all around the world, lost their lives on the Thailand coastal resorts, the beaches. People went down. The thing about when a tsunami wave comes in, this wave, first of all, it actually sucks the water out, and you can see exposed kind of the foreshore and the seabed essentially, and people being curious before you can actually see the wave coming in. Like you can see now, people went out on the beaches and exposed and said, "It's all these fish flapping around," and unfortunately that was the worst thing you could do. And then the waves came in, and they were still around about sort of 20 feet. In Thailand, by the time they got to Thailand, 20, 30 feet, some of the tsunami waves, and caused an awful lot of damage there. So to kind of sum up how earthquakes can essentially kill you, you can use the word facts. So know the earthquake facts and go through that letters, F-A-C-T-S. So F for fires, power lines down, gas lines ruptured. A for avalanches and landslides triggered by the earthquake. C for the collapse of buildings. And T for tsunami. And as it says here, can strike far from the epicenter. And S finally for subsidence, caused by the effects of liquefaction of the ground. So, okay, let's go on to the next topic in this lecture. Can earthquakes be predicted? So we can think of prediction when we look at all geohazards, be they volcanic eruptions and now earthquakes. We think about, can we make long-range forecasts over the next few years, the next few decades, the likelihood of a major earthquake, and short-term forecasts over the next few days or weeks with the likelihood of an earthquake occurring. Can we actually forecast that event? So long-range forecast first gives the probability of a certain magnitude earthquake occurring on a time scale of around about 20 to 100 years. So quite a long, long time period or more. It's a probabilistic assessment, so it's a statistical measure of probability of an earthquake occurring. For example, there may be a 60% chance of an earthquake occurring in the next 50 years, say, or a 30% chance of occurring in the next 10 years. Based on the premise that earthquakes are repetitive or cyclical, they have this recurrence interval, and that is sometimes a bit of a premise, but generally we see actually earthquakes can be basically in a large fault. Once an earthquake happens, stress is released, and then gradually stress is built up as there's more strain on the rocks over time, where the fault continues to want to move due to crustal extension, for example, or from or a strike-slip fault, like the San Andreas, a side-by-side motion of two continental plates in that case. But based on the premise that earthquakes are repetitive, they have a recurrence interval. So it's a cycle of build-up of stress, then you have the earthquake, build-up of stress, then you have the earthquake. And we went through that in the lecture prior to this. Use how we build up this recurrence interval. You have to use historical records firstly, but also you go back into the geologic record. So you use paleoseismology, paleo meaning ancient records of seismic destruction, seismic waves of earthquakes, are important because they provide information used to develop building codes and assist in land use planning. If you know the history of your area is prone to large earthquakes, you can therefore use that in your town planning. Decide not to build on areas of soft mud beside the foreshore of water bodies, for example, or lakes, and sort of zone the area, in other words, in terms of hazards, and decide what type of buildings are on different types of area as well, be they residential areas or just commercial property, for example. So here's an example. This one happens to be from earthquakes which strike the Middle East, in this case Israel, and the Dead Sea Rift Valley, so between Jordan and Israel. And here you can see, going through this rock record here, this sediment pile, you can see this layer which has been all kind of deformed. And basically what's happened there is what's called soft sediment deformation. And this former lake bed, at that point in history, there was an earthquake, and it all got folded around from ground shaking, and the muds were kind of convoluted and have this pattern. So if you happen to have a bit of wood in there or something you can date, you can radiometrically date it, radiocarbon date it, so you can get, in other words, a date for that earthquake, be it 500 years ago, be it 1500 years ago, 3000 years ago. And if you do that through the whole sequence of something like soft sediments like this, which are prone to deformation from earthquakes, you can then get a history of earthquakes and a recurrence interval. Then what's the average time interval between large earthquakes? So this recurrence interval, how do we reconstruct a recurrence interval chart? Well, you need as much data as possible. Generally, the more data you have, the better, and the longer time period you have, the better, and the higher resolution for that time period, the better. So you estimate the magnitude of all known earthquakes for a given area, so how large it is, which is hard. And, documented records are much easier, the amount of damage that occurs in an area. Once you get into the geologic records, a lot harder. You have to kind of the relative amount of damage you can see. Obtain dates for those events, and then you sort the data and plot it. And if you do that for an area, for example, here, the area of the map here in Northern California around the San Francisco Bay region, you can then, we'll come back to that and think about recurrence intervals. Before that, we're going to look at another type of phenomena which relates to long-term earthquake prediction, and these are things called seismic gaps. And this is where you have a long fault in an area, such as the San Andreas, and where parts of that fault so especially these strike slip faults. Parts of those faults become what we call locked or locked fault segments. And these locked segments we know are likely to produce a major earthquake, a future earthquake. So some parts of the faults have their earthquakes, the stress builds up, the rocks deform, then the friction's overcome and you have your earthquake. Other parts of that fault, certain sections of it, you're not having any earthquake, but there's still just as much stress going on, and at some point it's going to give along that fault line, and you will have a major earthquake at that point. So this is from an old journal article from the 80s, this figure at the bottom here, and it relates to where will the next quake be along the San Andreas Fault. Look at the gaps, the seismic gaps, and the San Francisco gap is still there. So here the cross section along the San Andreas Fault showing seismic activity 20 years prior to the 1989 Loma Prieta 6.9 magnitude earthquake. So from 69 to 89, all these earthquakes. So during the 60s, late 60s, through the 70s and 80s, all these symbols are dots, if you will, are focuses for earthquakes underground. So this is the vertical scale on the left, and so they're all happening at depth. But you can see they're clustered, especially around this middle part. And yeah, to give you some where this is, so from the east side or the right-hand side, you're going from south, and you go to the left-hand side is to north. So it's a south-north transect. So the south end is near Los Angeles. Parkfield's just north of Los Angeles, a suburb of Parkfield, small town. Then you move north. There's the Loma Prieta, which is south of San Francisco on the left there. Okay, so lots of small earthquakes occurring. So there's lots of stress being built up but released in that middle section. But there's, I would say, prior to the Loma Prieta earthquake, there's three gaps. There is a gap, so there's less earthquake being measured, small earthquakes have been measured around the Parkfield area, so there's a gap we could call. So there's less concentrations of earthquake foci. There's a gap also in the Loma Prieta region, sort of south of San Francisco, and there actually San Francisco Bay region itself. So let's call it three seismic gaps. Well, 1989 came along, and we had the 1989 6.9 magnitude, and the whole of that gap was filled in. It looked like the area to the right. Lots of small earthquakes, foreshocks, aftershocks, the main event itself, they all happened. Go fast forward into the 1990s, firstly in 1994, and then another bigger one as well in 2004. You had a lot of earthquakes in the Parkfield area, especially in 1994. So you had that gap was filled in. What's left? On the left, San Francisco Bay itself. So it's the actual city of San Francisco. Still hasn't happened. Has not happened. They've been talking about the next big one, as comparing, I suppose, the 1906 event. Still hasn't happened. Stress is building up in that section of the San Andreas Fault. There will be at some point over the next few decades. Could be next year, could be in 20 years' time. We don't know. In that region, though. And because it's been building up for a while, the likelihood is going to be a very high magnitude earthquake as well. Okay, going back to the probabilities, recurrence intervals. So here's the area, it's data from San Francisco Bay region looking at recurrence intervals. So here's data showing the timeline from sort of 1850, 1830, or through till past the year 2000 in this case. And the different bars here being the larger bars, being the columns being the larger earthquakes or magnitude earthquakes. So 6.8, 1938. Then 30 years later, 6.9. Then about 40 years later, 7.8. Then about 70 years later, an 86.9. So on average, you could say, I don't know, about every 40 years, there's a very large earthquake. So using this data, we can then say there is a probability of, the cyclical nature of earthquakes, of a large earthquake occurring. And this is what they did a while ago now, but they said there was, back in 2003, a 62% probability for at least one magnitude 6.7 or greater earthquake to strike the San Francisco Bay region itself between 2003 and 2032. Still hasn't happened. So now there might be, an 80% probability of happening in the next 10 years or so. So that probability is going to get greater. There's a strong chance of a large earthquake occurring, in other words, of the based on recurrence interval, the San Francisco Bay region. You can use that. You can think of probabilities as well of occurring by that date, in this case 2032, in each of the faults, because it's not just the San Andreas fault. The San Andreas fault also has several smaller faults kind of running off from it, stresses and fractures in the Earth, still related to that transform fault boundary between the Pacific plate and the North American plate. But there's also a very active one called the Hayward fault, and that's where actually there's movement. We think is actually very small on this map. The largest probability of movement occurring along the Hayward, so on the Oakland side of the bay. So this is from this data is freely readable on the U.S. Geological Survey website, by the way. So here you can see you can actually put different scenarios in on the website, on the USGS website. So earthquake planning scenario. Here's the hazard evaluation map for a 6.7 magnitude earthquake in the San Francisco Bay region. So it's a hazard map. The red's showing the highest probability, in this case on the intensity scale, and it goes up to the intensity 9 or 10 in this point in the reds, where you get significant damage. Again, along that Hayward fault in particular. Okay, so can earthquakes be predicted? So, you know, we've used, especially on a short term, we can use recurrence intervals, we can use seismic gaps. But what about short-term range predictions, which is obviously very useful, you know, so you can get out of there, or would be the ideal to evacuate an area if you know there's a very large earthquake going to happen. Therefore, it reduces the probability of you being damaged to zero if you're not there, essentially. Or to take measures, or to get to, or you have a very short prediction to get to an open area out of a building, for example. So the goal is to provide a warning of the location and magnitude of a large earthquake within a narrow time frame. That's the goal for short-range predictions for earthquakes or any hazard, actually. So it's a warning of the location. Where's it going to happen? How big is it going to be? And when is it going to happen over the next 2 weeks or week, whatever? Tell me a day if you can. And there's lots and lots of money gone into this from different countries, especially the United States, in California, but also in other countries like Japan. So the researchers concentrated on monitoring possible precursors, which are phenomena that precede a forthcoming earthquake, such as measuring the uplift or subsidence of the ground and strain of the rocks. Remember, these rocks, before an earthquake, are under a huge strain. They can be deformed as the earthquake, as the rocks are deformed along each side of a fault, going back to that elastic rebound model of an earthquake. And you can try and measure that deformation. So use things like tilt meters on the ground, like we did for volcanoes. Look at things if rocks are being, their density is changing, their physical properties are changing across a fault line. That'll be picked up on things when you let an electric current flow. So you can use something called a resistivity meter as well across a fault line. So there's lots and lots of work's been done around the world, but especially places like the United States, in California, to measure, and other countries like Japan and China, to measure or look for possible precursors, because you want that goal. You want a short range predictor of an earthquake. So we're looking for things we can use in the future to predict earthquakes, just like they've done for volcanoes. So use tilt meters to measure deformation of the surface. Use water levels in pipes. Water levels, when there's movement and fracturing of the subsurface, that's going to affect the water table level. And if you're monitoring the water table level, that can be a sign if it's moving up suddenly or down of movement underground in a possible earthquake. Fracturing of the subsurface can allow gases to escape, especially something like the gas radon. So you look for radon gas levels in an area, again showing possible movement of the subsurface, just on small degrees. Electrical resistivity, changes in the structure of the rock across the fault line. You can get different readings for that possibly. Foreshocks, so using seismograph networks to look for measure foreshocks before an earthquake. Animal behavior here. Some countries, they're still completely avid that this is a reliable way. For example, especially in China, for example, livestock like cows lying down en masse all of a sudden shows they think, or some people think that that's a sign of an impending earthquake, that they've got this kind of sixth sense of an earthquake about to happen. I'm not going to argue with that at this point, but it is one of those precursors that some people go along with. Can we currently make dependable short-range predictions? The answer is no. All these techniques, loads of money has gone into in different areas, especially, for example, in California in the San Andreas Fault, and setting up networks of monitoring equipment and experiments to look for earthquakes. But do they predict the earthquakes that occur along that region, say the San Andreas? No, they haven't. They have not picked up on these measures have not picked up on earthquakes yet. For example, something called the Parkfield experiment. So relating to the earthquake that took place in the Parkfield region we knew back in the sort of 1970s and 80s that there was the likelihood, based on recurrence intervals, there's going to be a large earthquake. So they knew already the knowledge of recurrence intervals back then. Let's put a load of equipment down there, a lot of scientists, and gather a lot of data and monitor that area. So the hypothesis back in 1985, moderate-sized earthquakes of about magnitude 6 have occurred in the Parkfield section of the San Andreas Fault at fairly regular intervals: 1857, 1881, 1901, 1922, 1934, 1966. So every couple of decades in that region, that specific region, the Parkfield section of the San Andreas, there'd been a large earthquake. So the available data suggested that all 6 moderate-sized Parkfield earthquakes may have been characteristic in that they all ruptured the same area in the fault. So if such characteristic ruptures occur regularly, then the next quake would be due before 1993, following the 1966 one. So therefore, let's monitor that area. We know one's coming. We think it's going to be before 1993. So that's what they did. So that says the prediction, the approximately regular cycle of these magnitude 6 earthquakes led two scientists in the early 80s to forecast that another magnitude 6 earthquake would rupture the same segment of the San Andreas Fault at Parkfield within 5 years of 1988. So within the next 5 years. This long-term prediction was evaluated, endorsed by the National Earthquake Prediction Evaluation Council in 1985, and the state of California was notified by the U.S. Geological Survey that there was a high probability of a magnitude 6 earthquake in the Parkfield region in the 1985-1993 time window. And the Parkfield experiment, involved more than 100 researchers at the U.S. Geological Survey, collaborating with many of the universities in that region and government laboratories. Their coordinated efforts have led to a dense network of instruments poised to capture the anticipated earthquakes and reveal, that was the hope, the earthquake process in unprecedented detail. So they knew it was going to happen. They knew roughly when it was going to happen. They knew it was going to be a big one. Let's monitor, monitor as well as we can that region, and let's see if we can find some precursors that work. That was the aim. The Parkfield experiment. 1993 came in that the end of the 5-year window. No earthquake. So the temporal element of this long-term prediction, they were saying it was predicting it would be within that time interval, failed. It didn't happen. Then finally, not until 2004 was the large one, the Parkfield one, there was an earthquake. So a long time later. And it was a large earthquake took place then, a magnitude 6.0. It says here at the top. Okay, so in other words, the predictions didn't work, and going back to that slide, the Parkfield experiment, none of the precursors were picked up on. It just happened in 2004, and none of the monitoring of gases, of tilt meters, everything else worked, unfortunately. So people now think, short-term predictions, will it ever be possible for earthquakes? Are they just completely random with no real precursors? to a degree, and some scientists actually think it'll be, it's a holy grail we'll never find. But there is a system for giving you a few seconds warning, and I'll talk about that now. Maybe a minute at maximum warning. It's all to do with the different speeds of seismic waves. So the early warning system, developed in Japan, provides a 20 to 60-second warning for locations away from the epicenter. This warning is issued after the actual initial earthquake takes place at the focus, at the main epicenter, wherever that is, even if it's offshore. In the case of Japan, the subduction zone usually. And then what you do, you monitor the arrival of the P waves and the S waves. So the bottom right diagram shows, if you look at the slides, it's behind the photo of me here, but if you look at the slides afterwards, you can see that basically there's an earthquake occurs on the at the subduction zone offshore from Japan in this case, and you first get the P wave traveling much faster than the S wave, and then the surface wave behind much slower. So once you monitor those P waves and you relay it up to satellite, then down to ground stations, and you give warning to people, you know the P wave will be so many seconds behind the S wave, which will be so many seconds behind the destructive S surface wave, and it's the surface wave that will do all the damage. You can then basically give a warning of 20 seconds, 30 seconds, 40 seconds, depending on how far away you are from the epicenter. The nearer you are the epicenter, the less the warning time, of when the surface wave will reach you. So the P wave's got to you, you know it's going to be another 20 seconds before the S wave gets there. So this is a really good, it gives you 20 seconds. What can you do in 20 seconds? Well, you can actually do a lot of things which will save lives. So what actions can be done? First of all, as a city, you can shut down trains and other mass transit. So for example, in places like Tokyo, places like now San Francisco, Los Angeles, mass transit systems, underground mass transit systems, the trains there are all hooked up to this early warning system, and they will be immediately switched off, essentially, and those trains will stop. In other words, you're stopping derailment. You've got 20-30 seconds to stop that train, just about enough time to stop the train very quickly, these small trains in mass transit, and you then save lives, because the derailment of a train is obviously going to cause an awful lot more deaths than a train train carriage which is stationary and just moving. You can shut down the electricity grid, so you don't have electrical caused fires. You can shut down gas lines, gas pipes, gas mains, so you don't have so much fire caused by ruptured gas lines. Yes, there'll be some gas in the system, but then it'll run out quickly, if you will, if it's been shut down at its source. You can notify first responders. 20 minutes, get in your trucks, whatever. Get ready to go. It's about to happen in 20 seconds time. That will save lives, precious seconds. Individuals such as surgeons in a hospital and emergency room personnel, they can be told, imagine someone's undergoing open heart surgery. For the surgeon, get the scalpels out of that person. We don't want to cut a major vein artery. So they all have apps essentially on the phone these days, or pages, to do that. So people in these regions now, just you and I can sign up to an app on our phone that's linked into this, and maybe for a small charge subscription, to link into this early warning system. So it gives people time to prepare, and you can think about that, what you can do in a building. If you know it's 20 seconds, you're on the ground floor, get out of the building as fast as you can. If you're on a higher floor though, you may not be able to get out, so the advice is to hide under get under a sturdy table is the current advice. It used to be under a door lintel, the arch of a door, that people used to say do that, but buildings these days aren't that strong, and the walls will probably collapse, so be under a large sturdy table, so if the building does collapse, hopefully you can be in an air pocket, which can emergency people can finally manage to get you out of there. So that's the advice. And you can do that sort of thing if you know 10 seconds time there's going to be an earthquake. Let's quickly either get out of the building if you're on lower ground floor, or find a safe space in your building. Okie dokie. So So here's an image, by the way, of San Francisco, a beautiful city, by the way, I think. And which is the last part of this lecture, we're going to very quickly, just 5 minutes, ask what can we do and what can you do? So what can we do as a community? What can you do as an individual? First of all, what can we do? We can be more aware of active faults. So through surveys of the area, geologic surveys of the area, be aware of which areas are more prone to earthquakes. Be aware of dangerous places to build, such as in that Oakland's disaster. So areas which are more prone, for example, underlain by soft sediment, so that likely larger amplified seismic waves. Design better buildings, importantly, and utilities, and so raise and enforce building codes for buildings. Retrofit old buildings. Older buildings can actually be, you don't have to build a brand new building sometimes, often. You can just do very simple things, which I'll show you in a slide or two's time, to simply strengthen with small changes to strengthen that building. Practice emergency response as a school, as a workplace, as a community, and have a drill of what to do in the event of an earthquake. Related to that is public education, again, of what to do in an earthquake, both during and afterwards. And continued support for research into this. It's continuing research. Hopefully one day we will get that holy grail of being able to do a short-term, we'll find a precursor that works for short-term earthquake prediction. It will certainly save lives if we can. This shows how buildings kind of collapse if they don't have any earthquake-proof structure to them. For example, this timber frame building, you can see if there's no diagonal braces, as we'll see, it'll very quickly from side to side motion simply just collapse to one side and it'll fall down. But if you have diagonal members, that will immediately strengthen that building just from adding, and you can do that when you make the building, but also you can add things like these L-brace bolts at the bottom of members, and you can foundation bolts, etc. And these simple things can be done afterwards, called retrofitting of a building. Seismic retrofitting will strengthen your building. Here's seismic retrofitting, the addition of these shear trusses on a university, California University, which is, I think this building was built in the 1960s. It originally didn't have these diagonal members, but they were put in at a later date to strengthen it. So these days, certainly since the 1980s onwards, instead of having building codes for just en masse for all buildings, so here shows on the left 1955 required strength for new buildings. There is sort of not that much, strengthen them a little bit. 1970, okay, let's strengthen most buildings considerably as far as how they're structured. So the structural engineers really design buildings now in earthquake-prone areas to withstand shaking. And then from the 80s, especially after the Loma Prieta, late 80s earthquake, there's building codes for specific zones of an area. For example, areas underlain by hard rock, as opposed to areas that are underlain by soft clay. So structures on areas of, say, for example, bay mud, soft unconsolidated sediment, have to be really a lot of money go into, or more resources go into designing that building, because we know it's going to undergo a lot of ground shaking or movement of the ground during an earthquake. What can you do to prepare? Choose your home wisely, I would say, especially the location of your home. Going back to looking at geologic maps, maybe if you can. Don't put, but simple things, don't put heavy stuff up high. If you're in a kitchen, whatever room you are, but let's say the kitchen, things are going to move off those shelves. So if you're in an earthquake-prone area, maybe don't put all your, your canned tin goods up high. Secure gas appliances. Secure them so they don't break easily. Know how to shut off the gas, importantly. Many people don't know how to, but know everyone in that household, in your family, take it as a responsibility to know that, make sure that everyone in your family knows how to shut off the gas, especially if you live in an earthquake-prone area, and everyone knows how to shut off the electricity. Where's the main switch and the main for the water as well. Buy or make an earthquake kit. You can either just buy the individual bits yourself, or you can get pre-packed earthquake kits from supermarkets, from Walmart, essentially, including supplies for at least 48 hours. At least you have to know that first responders might not be able to get to you for at least 2 days. So have a couple of days worth of provisions, in other words. I'm not going to go through all these items, but here's do go through them there yourself. It's just all sorts of advice on what to do. For example, secure top-heavy furniture to wall studs with metal braces, so your wardrobe doesn't fall on you. Use flexible connectors where gas lines meet appliances, so flexible ones that won't break, in other words. Keep fire extinguishers in accessible places. Keep heavy, unstable objects away from exit routes, anchor wheels, etc. All right. During the earthquake, don't enter or leave a building. So actually, during the earthquake, when it's happening, that's it. You stay in place or find somewhere. Get under a sturdy desk or table is the advice. So I always think maybe not an IKEA table. Actually, they can be quite sturdy, but get under an old sturdy desk or table. Keep away from power lines if you're outside. They can be snapped from the ground, expanding and contracting. If driving, pull over, so stop driving and stay away from bridges, because bridges can also be collapsed. And guides always say don't panic, which is easier said than done, obviously. And it's lastly but not least, you hope you are just simply the lucky one, that you'll get through in one piece. After the earthquake, prevent any fires, prevent flooding. Don't flush until sewer lines are checked, or you'll get a nasty surprise in your toilet. Evacuate buildings if necessary, but don't use the elevator. Use the stairs. Aftershocks are a distinct possibility, so do not go back into that building. That building may have been damaged to a degree. Just one small or large aftershock will make it collapse. So do not go back in to get your laptop that you left there or something like that. Wait until you're permitted to go back in, whatever point that is. Lastly, just giving you an example of different things you can have in an emergency preparedness kit that you can buy online or buy at a supermarket often these days, in these sort of earthquake-prone areas. It's got flashlights, emergency blankets, food to last for a couple of days, water pouches, importantly, things like duct tape, whistles, if you are trapped under a building, things like toothbrushes and toothpaste. If you're in an area which is it's going to take a while for people to get to, etc. All right, so there's sort of typical on the American Red Cross in this case. They produce them, so you can go on their website and buy them in this case if you're there. But all around the world you can get these earthquake preparedness kits. Okay, finally, here's an image of San Francisco in 1878 at the top, before the earthquake. So there it was. There is in 1906, a blaze after the earthquake, the great earthquake of 1906 in San Francisco. So the same city, here it is now. Well, in this case, 115 years later or thereabouts, depending on when you look at this. And I've been there for a conference once, and I thought it was a beautiful city, by the way. I don't know if you're watching this, you've been there, but it's a good city to go and go for a visit. But it is in danger of a large earthquake. But be aware that the buildings in San Francisco have got incredibly high building codes. So don't let it put you off visiting San Francisco, is my point. Also, that's a San Andreas fault. I just wanted to mention there's also a large earthquake possibly due in Turkey. There's a place called the North Anatolian Fault, which is also a strike-slip fault, which runs across the north of that country. And that has been transferring stress in this cycle from east to west towards the city of Istanbul, which this background photo, one of the main mosques in Istanbul, shows here. And we think in the next decade or two, there's going to be a large earthquake there in Istanbul, because the earthquakes are occurring one after the other along that fault. That's sometimes, rarely, it's one of the only places in the world really we can see this transference of stress along a strike-slip fault occurs, but we know it does occur along the North Anatolian Fault in Turkey. All right, I'm going to end it there. Thanks for joining, and I'll see you again. Thanks.